Hello, and welcome to this video on molecular orbitals and hybridization. My name is Ryan. I'm going to do my best to take you through all the concepts that you need to understand for this first chapter of organic chemistry pertaining to molecular orbitals and hybridization. So let's start off. Molecular orbitals, what are they? They're basically the things that electrons are withheld in. Electrons don't just fly around freely within around the atom. They usually have a confined space that you have a probability of finding them in. Molecular orbitals are held within shells, electron shells, around the electron. So we'll see in our first row right here, comprising hydrogen and helium, we'll have the one shell for the first row and an s orbital, okay? Now, the s orbital, along with the p orbital, can hold two electrons. So this hydrogen right here will have one electron, denoted by an up arrow. This helium right here, we would say it's 1s, it has one electron, two electron. Now when we get down to our second row, we're going to say that we're in the 2s shell. Okay, so 2 for the second shell, then s for the orbital that these ones will be in. Now lithium and beryllium, those have a max number of 2 valence electrons. So lithium has 1 valence electron, beryllium has 2. And so they could fit all those electrons within the 2s orbital. But once we get down to some of these electrons over here, they have more than 2 valence electrons, meaning that we're going to have to start branching out into the p orbitals, okay? P orbitals can also only hold 2 electrons, and given that there's 6 atoms here, we will have 3 different p orbitals, the py, px, and pz orbital. Now to get a kind of visual representation, we'll call this the s orbital and these p orbitals. So if we take an atom such as neon, right here, neon, we can see, counting its valence electrons, it has 8. We'd fill the s orbital all the way. We'd fill the p orbital all the way for each one, making a total of 8 electrons. Now let's talk about hybridization, okay? Hybridization, as the name implies, we're making a hybrid. So let's say we have an atom, or an orbital, an s orbital like this, and then we have a p orbital. And those two decide to combine, so they make a little bit of a funny shape like this, okay? So we have an s and a p, and those make an sp orbital. Okay, simple enough. But we don't have just one p orbital, we have 3 p orbitals. Whether they're filled up or not, we have 3 p orbitals. So if we imagine an s and 3 p's combining together, we'll get something like this, and we'll call it an sp3, right? That's pretty simple. It makes sense. And this orbital right here will do bonding with other orbitals of other electrons, making covalent bonds, okay? So let's imagine for a second, go down here, let's imagine we have a carbon atom, which is represented by a C, and we have an sp3 orbital. And remember, we're going to have 4 of them, because we started with 4 orbitals and we end with 4 orbitals after hybridization. But instead of having 1 s and 3 p's, now we have 4 sp3s. So we have a really bad looking sp3 orbital, didn't do a good job drawing it. And we have another carbon that holds an sp3 orbital. And this one, this has an electron, this has an electron. They decide to bond together. That makes a covalent bond. And the bond between the two is called a sigma bond, denoted by the Greek letter sigma. It kind of looks like that. And a good rule of thumb is every bond between atoms, unless there's a double bond or an extra set of lone pair electrons making a charge, so unless there's a double bond or a charge on the atom, the atom will have all sp3 bonds. That's a very good rule of thumb. You could assume sp3, and then you see a double or a triple bond or a charge on the atom. Now, what would be a case where we don't have sp3? That would be in a case of maybe a double bond. So double bonds, those are called pi bonds. And what those are, they're essentially unhybridized p orbitals that decide to overlap with each other between different atoms, so maybe between a carbon and a carbon, in addition to the sigma bond. Okay? So, seeing this visually, we could have a carbon and a carbon. We could have a sigma bond between the two. And then if we decide to add in a pi bond right here, that pi bond would be between two unhybridized p orbitals. Okay, so now that we have one p orbital being used for the pi bond, this carbon only has two p orbitals left out of its three. So that means that this sigma bond will be sp2 hybridized instead of sp3. Okay, now let's talk a little bit about geometry of atoms. Let's say we had an atom or a molecule such as this, C double bonded to the O, oxygen. Oxygen will have two lone pairs, and it has some H's right here. Okay, well, we could see that this double bond right here, that has a pi bond within it, so we could label one of these as pi, the other one as sigma. And given that one of the p orbitals is being in use, the sigma bond is going to be sp2, as well as it'll have an sp2 orbital here, bonding to the s orbital of the H, and an sp2 to s orbital, okay, for sigma bonds. Now this shape right here, this actually kind of makes a triangle. That is called trigonal planar, okay? So now we can understand sp2 makes trigonal planar. We're going to start filling out our chart over here. We'll put sp2 in the middle. sp2. The geometry is trigonal planar, like a triangle. Okay, if we go back to the molecule, we'll see that because the atoms, the H's and the O, they all want to be as far away from each other as they can. So to give an equal distance between each of them, there's going to be a 120-degree angle between these two, for all of them. So we could figure out our bond angle is 120. And this right here, number of bonded atoms and lone pairs. That's actually what we should be starting with, okay? So if we count the number of bonded atoms and lone pairs for this carbon, we see that it has 3 bonded atoms, the O and the 2 H's, and the carbon has no lone pairs. So we'll just write in 3 here. Okay, now let's do another example. Let's say we had a methane molecule. Methane is just C with 4 H's. Now let's start off by counting the number of bonded atoms and lone pairs. We see that there's 4 H's bonded with no lone pairs. This is a neutral charge. Going back up to our table, we could write in 4. And given that there are no pi bonds or lone pairs, we could assume that the hybridization is sp3 for that carbon. Now, talking about geometry and bond angles, this carbon, what it would look like in 3D space, not in a linear fashion, we'd have our carbon atom. Maybe we have an H going up and an H going over to the side, an H going towards the back, that's what those dashes indicate, an H coming out towards the front. Okay. Now the bond angle between each of these is going to be 109.5 degrees. We'll call that tetrahedral because there's 4 things bonded. Tetra means 4. It makes sense. We'll write in 109.5 and tetrahedral. Finally, Our last example will be of an atom that has a triple bond. So we'll do C triple bonded C. Again, we have one sigma bond right here, along with two pi bonds. There'll always be at least one sigma bond. I'll label the bonds themselves, they're right here. Okay. Each of those two pi bonds is taking away an available p orbital from this carbon, meaning that this carbon will be sp hybridized because there's only one p left. sp hybridized. There'll be an H here and an H here. And because there's only two atoms bonded to this central carbon, right? We could fill in our chart that when we have two atoms bonded, we have sp hybridization. There will be 180 degrees between each of them, and we just call this linear. One little trick to remember this is that for the number of atoms bonded plus the number of lone pairs, so two lone electrons makes one lone pair, that'll count as one. So the number will equal the number of letters, right? So 2, S, and P. 3 is S, PP. 4 is S, P3. It adds up to the number. So that is just a basic understanding of molecular orbitals and hybridization. I highly advise that you go through your homework labeling the hybridization of every atom in a bond. That'll give you some good practice of understanding the hybridization as well as bond angles and geometry. Thank you for watching this video, and we hope you'll tune in for more videos in the future.